Muy buenas tardes a toda la comunidad de Ingeniería de Sistemas. Estamos siguiendo con nuestro ciclo de seminarios ya a mediados de noviembre. Tenemos un ponente especial, no le conozco personalmente, pero estamos haciéndonos amigos aquí. Está trabajando en donde yo solía trabajar, con personas con quienes yo solía trabajar, y tiene trabajos súper interesantes. Pero déjenles, voy a ceder la palabra a Gerardo Palafox para que les cuente más sobre el doctor Alexander. Adelante, Gerardo.
Gracias. Hello, everyone, and welcome. Joining us today is Dr. Alexander Jung. Alexander received a master's degree and a Ph.D. degree in electrical engineering and signal processing from the Technical University of Vienna in 2008 and 2012, respectively. He's currently an assistant professor for machine learning at Aalto University and serves as an associate editor for IEEE Signal Processing Letters and chapter chair for the IEEE Finland Joint Chapter of Signal Processing and Circuits and Systems. He has received a Best Student Paper Award at IEEE International Conference on Acoustics, Speech and Signal Processing in 2011, an Amazon Web Services Machine Learning Award in 2018. He was chosen as the Teacher of the Year in 2018 by the Department of Computer Science at Aalto University. Professor, welcome, and go ahead.
Thanks a lot, everybody. Can you see my screen? Yes, so today I will talk about networked federated multitask learning. This is one of our main research areas. Just to quickly add to the introduction, which basically covered my bio so far. So I'm leading the research group Machine Learning for Big Data. And we have two main research areas at the moment. The first one is the theme of my talk today, network federated learning. And the second main research area is explainable machine learning. So we look into methods that can explain or compute explanations for the predictions that we get from a machine learning model. And these explanations can be of very different forms. So the explanation could be a relevant example of a training set, a previous example, or a subset of features, could be a counterfactual or a free text explanation. And so our take on this explainable machine learning is from the perspective of information theory. So we want to construct explanations to maximally reduce the uncertainty or the entropy of a prediction that we get from a machine learning model. So, and using these information theoretic concepts allows us to talk about or to define optimal explanations and to design methods to compute optimal explanations. So this is the second main research area we are looking at the moment. Then I would just quickly highlight my efforts in teaching. So we have set up several machine learning courses. And the most recent one has been enrolled by around 1,000 students from all over Aalto. So we have students from all kinds of different fields. And to cope with this heterogeneous student background, I have developed a teaching concept for machine learning, which is based on three components: the data, model, and the loss. And so this teaching concept and the materials are now soon released as a textbook for machine learning. And you can find the draft also on my webpage as shown here. But now, regarding the topic of today's talk, network federated learning, which is kind of a focus area at the moment. This is joint work with some excellent students in my group, Yasmin, Yu, and Linli. And the guiding principle, or the name of the game here, is to organize data and models as networks. So to use network models to process data, to learn from data. So networks are present in many different application domains. When you look at the internet or data generated by the internet, by all internet users, there is a clear network structure based on the connectivity in the internet. Weather observations have a network structure. The observations, for example, in Mexico City are somewhat similar to the observations in Monterey and less similar to the observations in Helsinki. So there are this similarities relation, and this is exactly what gives rise to a network structure. Another example for network data are publications or scientific articles where you have similarity relation between articles, for example, based on the number of co-authors. So if you have two papers with a large number of the same authors or a large set of intersection of the author list, then they might be similar. A somewhat unusual application domain of networks, or not so much anymore, is medicine, where we look at networks, for example, of different diseases. So here's another example for a network structured data set, images. So maybe some of you have already worked with the ImageNet database. So this is a database that consists of many images, and these images are not completely random or an unordered set, so to say, but there's a structure present in this ImageNet data. And this structure is given by a network structure which is called WordNet. And this WordNet is a taxonomy that relates the different objects of which images are shown in or are present in the ImageNet. For example, one object is dog, and there are different species of dogs like border collies or boxers and so on and so forth. So here in this ImageNet, there's a clear and significant network structure present. Another example that you might know is Wiki Data. So I guess many of us use Wikipedia on a daily basis to gather information, to get information. And the information provided by Wikipedia articles is often based on a data that is stored in a Wiki Data. So you can think of Wiki Data as a database, and this database is structured as a network. So you have different items or data points in this Wiki Data. For example, San Francisco could be one data point or local data set, let's say local data set. Another local data set could be everything related to California. And these two data sets are related by, it's called a predicate. It's called a property in this language of Wikidata. It's a property which is San Francisco is a city in California. So you have here a relation, and these relations, which are the properties between different data items, they give rise to a network structure. Another example that I already mentioned are diseases, where you have each node in the network represents a disease, and also all the data we have about a certain disease, different articles, scientific articles, or healthcare records of persons or patients that have been diagnosed with a certain disease, like a coronary heart disease. Then there's another data set of all healthcare records for people which have a cerebral infarction, and so on and so forth. And these individual local data sets that represent diseases, they are related by a network structure, which is given by the co-occurrence of or comorbidity of these diseases. So if two diseases occur often together, so patients have have often this disease and this disease together, we connect it by an edge or a link in this network. And then we might use tools from network science to find clusters of similar diseases, in some sense similar diseases, and we might then have the hope to be able to use similar treatments or drugs to treat all these similar diseases. Okay, so this was the motivation from the application perspective, why it might be interesting to study network data. Now we look a bit into the modeling of network data. So in our case, or in our work, we use a graph, an undirected graph that we call the empirical graph, to represent such network data. So each node in this empirical graph represents a local data set. And this can be vastly different forms of data sets. So a local data set could be a single measurement of a temperature sensor in a wireless sensor network, or this local data set could be all the digital information we have about a person like me, Alexander Jung. And there's a lot of digital information that I generate. Every time I go to the shop and pay with my debit card, there's data generated. Every time I have my phone running with Google, there's data generated. So Google has a lot of data about me. And this local data set, my local data set, is related to other local data sets, for example, to my family members, which have similar travel patterns. So their data sets are somewhat similar. And the similarities between data sets is encoded in the edges or links of this empirical graph. And we also quantify the amount of similarity by assigning a weight, a number, or some quantity, a number that indicates how strong is the similarity between two connected local data sets. Okay, so what we do typically with data, well, we fit a model to data. Data by itself is essentially useless. You can store it, you can forward it, but in order to learn something from data, you need a model. And here we use the same network structure, the empirical graph, to also define a model. So we define a networked model by assigning each node, each local data set, a weight or a parameter vector. So this vector is a vector consisting of parameters of some model, of some parametric model. Could be a linear regression model, or a generalized linear model, or a Gaussian Markov random field, any type of model that you can parameterize with a finite set of numbers. And what we then typically do, we fit the model to data. So we need some notion of a loss function. So this is again the three-component picture of machine learning. We have data, network data, we have a model, in this case network model, and then we need a loss function that allows us to find the good choice for these weights or parameters of the models. And this we assume we are given a local model. So we basically abstract all the details of how to come up with the model. This might be a time series model, an autoregressive model, or a Gaussian Markov random field model. Just some model for which we know, for which we have a loss function that we try to minimize in order to fit the model to the data set. Okay, and this, by the way, is then a form of multitask learning. We can interpret each of these local data sets and the task of fitting the parameters of this local model to the local data set as a learning task. And what we want to do is we want to solve all these learning tasks for all network nodes at once. So this is a multitask learning problem. And how can it work? I mean, if basically my rule of thumb that I always teach the students in the first machine learning course, try to have much more data points or a data set that is much larger than the number of parameters that you have. But here in the extreme case, we could have one parameter for a single data point, or several parameters for one single data point. So how can this ever work? Because now, intuitively, you would say this leads to overfitting. So we need some structure, some smoothness or clustering assumption for this to work. And here the clustering assumption is not the direct form that you will often hear or use in machine learning, which is similar data points should have similar labels, but similar data points should have similar models. So we want the parameter vectors. We assume that the good parameter vectors, in some sense optimal parameter vectors for these local models, are similar for nodes that are well connected. So here we have 3 nodes that are densely connected by links or edges which have weight 2. Here we have only one link which has an edge 1. So this is a weak link. These 2 nodes are weakly connected, whereas these 3 nodes here are strongly connected, would say. So we then would learn, or we then develop machine learning methods that learn similar parameter vectors for all these densely connected nodes. They form a cluster. And we do not know at the beginning, so we want to come up, or we want to design machine learning algorithms which do not explicitly find the clusters, which do not have to explicitly find the clusters, but somewhat on the fly, while learning these parameter vectors, also determine the cluster structure of this network data. And the way we approach this, or we try to solve this, is via total variation minimization. So we define a measure that represents the amount of variation of these weight vectors over the edges. So by enforcing this generalized total variation, this is a sum over all edges, and then each component in this sum depends on the difference between the parameter vectors of the connected nodes, and we want this sum to be small. So we want to minimize the total variation. And by enforcing a small total variation, we enforce the weight vectors, the resulting weight vectors that we get out of our learning algorithm, to be approximately constant over this well-connected subset of nodes or clusters. So two special cases of this total variation measure or generalized total variation measure are obtained for this penalty function here, the 2 norm. So I should say or discuss explicitly this generalized total variation involves a penalty function, and this penalty function is a design parameter. So you can choose different penalty functions phi, and you get different instances of general total variation. And this kind of whole class of generalized total variation includes at least two important special cases. One is the total variation, which is obtained from using the 2 norm of this weight vector differences. And another special case is obtained from using the squared Euclidean norm. And it turns out that if you plug in the squared Euclidean norm into the definition of the generalized total variation, what you get, this whole sum here, becomes the graph Laplacian quadratic form, which is also a very useful quantity for characterizing networks using matrices or using quadratic eigenvalues of matrices. So for spectral graph theory in a nutshell. Okay, so now we just need to plug together two components in our learning problem. So one component here is this generalized total variation term. This term measures the amount or the extent of clusteredness of the weight vectors. So if the weight vectors are of these local models are constant over clusters, then this term here is small. Whereas if they change a lot within a cluster, so they are not approximately constant over the clusters, what we would like to have, if this is violated, then this term here will be large. And we don't want this, so that's why we minimize. We try to minimize this term. However, we cannot only minimize this term, because this would deliver a trivial solution like all weight vectors equal to 0, which also has 0 variation trivially. So we also need to balance this with the loss functions. So we have, for each node, we have a loss function that is a measure for how good a particular choice for the weight vectors is. And our approach allows to have this loss function only for a subset of nodes. So we don't need to know the local data sets for all nodes, but only for a subset. And this can be a vanishing fraction of nodes, which is kind of a training set. So we need to access the local data sets only for a small subset of nodes. And this might be useful in many regards. In healthcare applications, accessing the local data set might require consent from patients. So, and not, for example, in this coronavirus tracking app, you need to explicitly download the app and give consent that it can use your phone, so it can be used. And there are many people which are hesitant to use this. So here the training set would correspond to all people which use the COVID tracker app, for example. Or in a vaccination trial study, this training set would be all the persons which take part in a study. And of course, in the beginning, only few persons take part in a study. But still, we could use this information, these local data sets from these few persons to generalize, to learn the models, the kind of the parameters for the local models for all other persons, for which we know how they are related to the persons in the study. For example, have similar biological or physical properties. Okay. So now we have a learning problem in the form of an optimization problem. How do we solve an optimization problem? Well, using some optimization method. But then, of course, yeah, here I also want, before I discuss this optimization methods, I want to point out the two special cases we obtain for specific choices for the general total variation. So if we use the Euclidean norm here to define the GTV, we obtain the network lasso, which has been proposed recently by a group in Stanford, Stephen Boyd and his students. Another special case is called the MOCA, which has been popularized in the machine learning and artificial intelligence community recently. And this special case is obtained from using the squared Euclidean norm for the GTV. Okay, so these are these two special cases, but in general, we look at this optimization problem with some penalty function phi. And then there's always two questions as a machine learning scientist. When you have such a learning problem in the form of an optimization problem, there are always two aspects, a computational aspect and a statistical aspect. So the computational aspect is, can we solve this problem efficiently and how? And the statistical aspect is, are the solutions any useful? So for example, when a model overfits, then it's nice if you can find the optimal model parameters, but they are useless because they just overfit the training set. So let me now discuss these two aspects separately with a focus more on the statistical aspects. But let's start with a quick summary of the computational aspects, which is not too detailed because it turns out this optimization problem, so this GTV minimization problem, which by the way is also an instance of a regularized empirical risk minimization problem, because this training error here is nothing but an empirical risk term, and this generalized total variation is nothing but a regularization term. So this is a regularized empirical risk minimization problem, and for many useful models, this is a convex problem because the loss function is convex, for example, for linear regression or for generalized linear models or for more general exponential families. This becomes typically a convex function. And for many useful choices for this phi, in particular the two special cases that I mentioned, this is also convex. So we want to minimize a convex function. However, this convex function is non-differentiable. So we cannot use gradient descent. But for such types of optimization problems, which consists of two terms, and each term separately could be minimized easily, but summing them together then makes it difficult to minimize it. There you can use primal-dual methods very efficiently. So the idea is to solve this optimization problem together with a dual problem. And I will not go into any detail of the dual problem, just to give you some intuition. Can represent a convex function like this objective here as a function of the weight vectors is a convex function, and we can represent the convex function by in two dual ways. So the first way to represent the convex function is to specify for each parameter vector or for each argument value the function value. So for this parameter value, I have this function value. For this argument value, I have this function value. So this is one way. This is the primal way to represent the convex function. And then there is a dual way to represent the convex function, which is as the envelope or the intersection of half spaces that are characterized by supporting hyperplanes. So you can you can obtain this function also if you kind of intersect all the, or if you compute the intersection of all the supporting hyperplanes at each point. And the supporting hyperplanes are essentially defined by the gradients or subgradients in the case of non-differentiable functions. So instead of specifying this function by this graph, you can also specify this convex function by specifying for each possible slope of the tangent what is the necessary intersection. And this intersection is called the convex conjugate of this function. And similar or this dual way to represent the function translates into a dual optimization problem, and primal-dual methods solve the primal problem simultaneously with a dual problem. So this then ends up in a very generic optimization method, which is called a proximal point algorithm, but I will not go into any more detail here. This is something you can then study by looking at the papers, or if you're interested in reading about convex analysis. So this is now would be too much detail, but just to point out, what we get in the end is a quite robust and scalable message passing algorithm. So this algorithm here amounts to passing messages. So it's an iterative algorithm, so it proceeds in iterations. So we repeat the steps several times, and in each step or in each iteration, we just pass messages between neighboring nodes in the data network structure. And yeah, it turns out that this algorithm can be implemented using only local computations, and then spreading the local results to the neighbors. So it's a distributed algorithm using local computations and message passing between neighbors. So this makes it scalable to large data sets with billions of local data sets, like the internet has typically. It also turns out that these primal-dual methods are quite robust against different forms of errors or failures. For example, these sub problems here in this message passing, they amount themselves to solving smaller optimization problems, and these smaller elementary optimization problems, they typically cannot be solved with arbitrary accuracy, but only to some tolerance. Yes, and what is also nice about this primal-dual methods is that it's rather easy or not too difficult to come up with stochastic versions which allow to reduce the complexity, the computational complexity. What do I mean by a stochastic version? For example, we do not do these updates and these local computations for all nodes in each iteration, but we only randomly select a small fraction of nodes for which we do the updates. So we can then save computation by this random sampling approach. And also we can use this random sampling also to handle node failures. So some nodes, some computational nodes that correspond to a local data set might just fall flat, so fail, cease to exist, and still these algorithms will converge with reasonable probability and accuracy. Okay. What is also pleasant about this message passing algorithm, it does not share raw local data. So nowadays, when you use machine learning, you always need to take care of privacy constraints, and this message passing algorithm does not share raw local data. It only shares updates of the model parameters. Of course, these updates, these updates carry some part of the information in the local datasets, but this is typically much, much smaller than revealing the raw local dataset to the neighbors. Okay, yeah, just here a quick overview or snapshots of recent papers on primal-dual methods. So this is still a vibrant research field, and it's also studied now exactly in the setting that is relevant for federated machine learning applications. That is large-scale distributed with failing nodes, stochastic versions, all you would like to have for designing efficient machine learning algorithm. Okay, but what received less attention so far is the question of how useful are the solutions of this problem. So what are the statistical properties of the solutions? Is this any good? And here one of our main results recently are sufficient conditions on the network structure, in particular on the clustering structure, such that this minimization problem here results in good parameter vectors. By good, I mean the solutions of this minimization problem are the optimal parameter vectors if the local data sets share a common optimal parameter vector. So if these local data sets are statistically similar. So under this assumption, kind of a ground truth, and the clustering is sufficiently pronounced, and we characterize the clustering by a flow, by network flows, then it works. So just to give more details, so the amount of clustering, or how much clustered the network is, we measure by the amount of flow that can be routed over boundary edges. So the more flow we can route over a boundary edge, and which is absorbed in some of the observed nodes. So this field nodes here, they represent the nodes in the training set. Those nodes are those for which we know the training set. So we translate the learning problem into a network flow problem, which is one of our key findings or key developments recently. And using this network flow approach allows us to characterize the cluster structure or the network structure such that the learning algorithm is successful. So we come up here, for example, here we have a visualization of our algorithm, in particular about the flow values that we use in our algorithm. And these edges, for example, these links here, they are boundary links. So we can say here's one set of nodes that are well connected. Here is another set of nodes that is well connected. So it seems to be two clusters. And our algorithm ends up with filling up. It's kind of a network flow optimization algorithm. So we fill up these boundary edges. We want to saturate these boundary edges. And if they are saturated and the other edges within the clusters have still room to carry more flow, but they don't need to because already these boundary edges are saturated, then our algorithm correctly identifies the cluster structure. And we have verified this analysis by some simple numerical experiments. So this here shows the mean squared error or normalized mean squared error of the solution of this GTV minimization problem as a function of the cluster connectivity. So the cluster connectivity here is a measure of the amount of flow that can be pushed through the boundary edges. And the more flow we can push through the boundary edges means the more connections are within a cluster. So the better connected the clusters are. And there's some critical value above which the cluster structure is so pronounced that our algorithm is able to lock in the correct cluster structure. Okay, and then of course the question is, I mean, this here, for example, this could be a toy example. So this is just a very unusual network structure for which by luck our condition is satisfied and it works. So we started also the question, how rare is this clustering assumption that we have on our method? And for this we looked into the parameter regimes of a stochastic block model. So a stochastic block model is maybe the most basic model of a clustered network, where we assume that the nodes are partitioned into blocks. So in this case, we have only two blocks. And the nodes in the same block, they are connected by independently drawing an edge, yes, between these two nodes with a probability P in. And two nodes from different blocks or different clusters are connected also independently with a probability P out. And for each block, we have access to the datasets on S nodes. So S is some sense the size, the sample size that we have observed or that we have access to. So in this case here, S would be 1. So we have one local data set at our disposal in cluster 1 and one other local data set in cluster 2. And then what we obtained is a threshold value for the ratio of P in to P out times this number of local data sets that we know. And it turns out that the threshold pretty much reflects, really surprisingly well, reflects the phase transition of the GTV minimization algorithm in practice. So these markers here show the actual or the measured, the simulated accuracy obtained from the solutions of GTV minimization using different settings for the stochastic block model. So we use different number of or different sizes for the training sets. So here we use S equal 5, so we know 5 local data sets in each cluster. Here we use 10 local, we know 10 local data sets in each cluster. And yeah, I didn't indicate this here. So each cluster consists of 50 nodes. And it turns out that this threshold here is exactly at 50 for this simple 2-cluster SBM. But we have a closed form expressions for the threshold that involve P in, P out, S, and the sizes of the clusters. So it seems we have pretty much accurately or precisely characterized the behavior of GTV minimization if the data is well modeled or can be well approximated by a stochastic block model. Okay, so to wrap up this quick overview of our work, so we formulate federated learning in network data as a GTV minimization problem, as a generalized total variation minimization problem. This formulation unifies several existing approaches for federated learning. So 2 special cases are the network lasso and Mocha, but this GTV minimization includes many other forms of federated learning methods. We showed that this GTV minimization problem can be solved quite efficiently using primal-dual methods for convex optimization, which are pretty well understood, and there's really a lot of work ongoing also to understand their stochastic versions and how robust they are when you implement those in a really large settings with a lot of different error sources like failing nodes, stragglers, which are nodes that are somewhat delayed in their updates. And we have already quite a good understanding of how these primal-dual methods behave in such harsh environments. Yeah, but our focus was on characterizing the conditions on the network structure such that this GTV minimization is able or is successful in adaptively pooling similar data sets into clusters. So that's what the whole federated multitask learning is about. We want to find the clusters of similar local data sets that we can pool together. And over this pool of similar local data sets, we do plain vanilla machine learning. We fit the model to all these local data sets in the same cluster. However, the problem is to find the clusters. And these GTV minimization methods find the clusters while fitting the model. So it's done simultaneously. It's not necessary to first do a clustering algorithm and then fit on each cluster, but we do it at the same time. Okay. That's all from my side. I'm now happy to take questions. And yeah, we have also papers available and implementations on GitHub. So we'll share the links with you later.
Excellent, Alexander. Thank you. I have so many questions because, as you might know, this is the kind of stuff I've been fiddling with in the past. The first thing I'm going to bother you with is the first thing people always bother me with first. Yeah. The math you have, it's usually really easy and straightforward, and everything kind of converges where you want it to go. when your graph is unweighted and undirected, because you have a lovely symmetrical adjacency matrix and everything is fine. Have you tried if you can make all of this work also if you have a weighted and directed graph? Because often the directed graph starts messing with the math because you don't have a symmetric matrix anymore.
Yes, very, very good question. So what we can handle easily are weights. So we have here in the GTV, we have this Aij, and this can be different for different edges. So what we can handle easily are weights, so weighted graphs. We didn't look into directed graphs. So my hope is, since we set up a machinery based on flows, and network flow methods are also somewhat understood for directed graphs, but I didn't look into detail. So my hope would be that this would be not completely hopeless, but we didn't look into this yet. But definitely very, very relevant question to look how do our results change if you have directed networks.
Yeah, many spectral methods start kind of getting funky when you go into directed graphs. So that's an interesting thing. And also, if you have multiple labels, like more than 2 clusters, I'm assuming you would do this hierarchically. Like first you split it in 2 and then you split it in 2. Do you feel that in practice this is a good way to go about it? Because my personal worry is always that if you have an error in the first division, then kind of like the whatever noise you had in the first one, it kind of propagates and messes everything up downriver, because the first split affects everything. Do you think there's a way to do this with like multi-cluster simultaneous, so that we wouldn't have to like have the impact of the first decision kind of like affect all the subsequent decisions on how the clustering goes?
Very good question. So the models that we looked at so far, these are really the simplest, a 2-block stochastic block model. We didn't look into such hierarchical graph structures like that you were referring to, and I don't know actually how to extend or how to take this into account, like I think this is called multi-resolution graphs. So you look at the kind of a bird's eye view, and then you open up more and more details. So you kind of merge nodes together to supernodes, or you open them up to the subnetworks they represent. I don't know. This is very interesting, and I think this is an important next step to really get practical methods to use such hierarchical concepts and hierarchical models. But
yeah, when you have a hierarchy, you sometimes also get like overlapping clusters.
Yes.
Because you're thinking like in an organization, like if you have a social network at a university, you basically have the departments kind of like meta nodes, but then there are people that are kind of like affecting in more than one department. So it kind of gets fuzzy at that point, that you might have a vertex that has like a different degree of belonging into more than one clusters. And then also in practice, you have the problem that the cluster sizes aren't necessarily comparable. You might have singleton vertices that don't actually belong to any cluster. And this has been in practice something I've often had to deal with my colleague Sarah, that you have a very lovely natural cluster, but then it has these like groupies, these hangarounds, like this little tail that hangs from the natural cluster, that if you ask the tail, they are definitely part of the cluster. But if you ask the cluster, they don't know the tail, because the tail, it isn't really connected densely to anything else other than the cluster. But from the internal point of view of the cluster itself, kind of like the stuff hanging from it, it's just parasites and it doesn't really go. So what's your feeling on how this will work if the clusters don't have in any way similar orders, that you have ones that are massive, others that are tiny, and then these kind of like hang around things, like let's say you have a huge click and then you have like a tail hanging from the click. So what would happen here? Would the tail be absorbed into the click?
Very good question. So actually what we do so far with these non-smooth optimization methods, in this really simple, nice two-cluster, well-defined cluster structures, you hardly can beat spectral clustering. So that's where spectral clustering is really what you should do. But when you have what you pointed out, these very vastly different cluster sizes, there I think this flow-based approaches, they could be better than spectral methods. When you have a very small cluster and a very large cluster, then when you look at spectral methods, as I understood, basically use the first few the principal eigenvectors of the Laplacian. So they leak out. So the eigenvectors corresponding to the large cluster, they also leak out to the small or tiny cluster. But and this could make problems for spectral clustering, but our approach is really based on flows. And if the flow, so if there's really a small bottleneck, the size of the cluster doesn't matter. It's just the bottleneck has to be sufficiently well defined. Then our method can find the small cluster, no matter how tiny it is, and it can even be a single node. So this is then an outlier if a cluster consists of a single node.
Yeah, I remember working with like flow and also conductivity-based models, because I really like thinking of the graph like an electrical network and kind of like having the current flowing there. The selection of the sources and the targets for the flow problem, they were pretty relevant, in especially when you had like different cluster sizes. It really matters where they go, because the further apart they are, the better bottleneck you get. But if your source and target are kind of like close to the natural bottleneck, it kind of starts messing up. Alberto has a very interesting question. In reality, when we model something as a graph, it's easy for us to fake that we take a snapshot, and that snapshot is kind of like representative of what's going on. But usually each node kind of like evolves, like the node has like an internal time series of its attributes. And sometimes the edges also, they kind of like show up or disappear or strengthen or weaken over time. Do you think it would be possible to adapt this kind of a situation to a graph model that isn't static, but kind of like you're doing the calculations like in an online or self-stabilizing manner, where you might get new nodes, you might get new edges, and you might get changes in the attributes of the existing ones? Can you still kind of like continuously learn this, or do you think it would degrade?
So very good question, and this is also on my wish list to look at, but of course time is only finite for me. This would be, so what I have in mind for this, and this is very important for the applications, how is it called, a multi-layer network. So instead of a single one, I would just like take this and copy it and get the next time step, get the next snapshot, so to say, and would connect few of them. Some of the nodes are connected also over time, and then, I mean, this would be just a bit more fancy network. So I would just draw a more fancy network, and I could still use all the methods. But the question is how to take into account this multi-layer structure, and I don't know yet.
It would be kind of cool to be able to kind of like in parallel to be clustering at all the different time steps, and then kind of having like a sparse information flow between those. Because if you can make this small enough, you could do it like in a GPU, that you have every single core doing its own, and then they just kind of like negotiate that from my point of view, these two belong together, but from this other guy's point of view, they kind of don't. And then some consensus type of a thing that if at most times they go together, then you think they are in the same cluster or something of that nature. That would be extremely interesting.
Yes.
My colleague Arturo has a little bit more of a meta question. I'm going to read it so I don't mess it up. If you have an application that requires the degree of similarity between, say, pairs of customers, the vector W actually represents internal degrees of freedom for each customer. But the dimensionality of such a space of internal tastes or preferences is usually non-observable. How would you go about estimating the dimensionality of the hidden space, kind of like the non-explicit information in the graph?
So the way, so our framework assumes that we have a parameterized model at each node with a given number of parameters. And what I was thinking already, but I don't know yet how exactly to do it, to abandon this assumption, which is quite limiting, just to have non-parametric models, like decision trees. So I don't know if this is related to that question, but yeah, at the moment, all I can offer is methods for finite dimensional parametric models. If I mean, you could these local models, they can be anything. So you can also have latent variable models. You just need to have a finite number of parameters and the same number of parameters for all local data sets. So this homogeneity in terms of the number of parameters or the dimension, I don't know how to get around this, because then how would you compare the weight vectors at different nodes if they have different lengths? So you would need to generalize, or you would need to replace this concept of a total variation, which is really convenient to do when you have finite parametric models, because you just compute the difference between the weight vectors. But how do you compute the difference between two models with different dimensions? So
some kind of a Jacquard thing, like the ones that actually exist in both, do like a calculation on those, and then kind of try to figure out how many things does this one have but that this one doesn't, and how many things that this one have that this one doesn't, and kind of like have like an uncertainty parameter that has to do with like the lack of overlap with the parameters present might work.
Yes.
Okay, one more idea that I have. In addition to networks usually evolving over time, our observation of them is unreliable at best. So have you tried that if you make your simulated graph, but then you don't actually give that graph to your system, and especially when you have like an ensemble method, like like the federated learning thing, that if everybody sees like a different version of it, that when you show the network to the parts of the learning family, that everybody gets like a slightly different distorted view. Everybody has their own local errors. Would this like the robustness to this? How much can you kind of distort the partial views and still get a coherent view out of the total calculation?
Yeah, so my hope is, without knowing this in any detail, but this known results of robustness of these primal-dual methods would kind of handle this. So this known stochastic analysis of these primal-dual methods, and these errors that I mentioned, which sounds a bit generic, various failures, various errors and failures. So one form of error could be a modeling error, because this network structure that we use in the algorithm is not the actual network structure in the data. So this would be one of these sources of error that I hope, or that I claimed, that can be handled, or that the primal-dual method is robust against. But how to measure, how to quantify this robustness, I do not know.
Well, very interesting. I mean, particular going over in my head, because in Alberto's doctoral research, we're working with variables of air pollution. And then we have like measurements of public health, like indices, like how many people are diagnosed with this and that. And you get these huge like causal graphs that these things seem to be related, that this thing seems to be causing this thing later on. And it kind of comes to a clustering problem, kind of like trying to figure out which things are linked amongst themselves, which things are linked with another one. But it is kind of like a multi-class, multi-label, evolving situation. And this might be an interesting way to go about it as well, because it's not like such a clean problem that a spectral method could really deal with it, because a causal network, it's almost always weighted and directed. So most spectral things kind of like fall apart there.
Yes. So one nice thing about this, our way to analyze this via network flows, the really decisive thing about the network structure are the boundaries. So if the boundaries, if the bottlenecks are well defined, then it's not so much important how the connectivity is within the cluster, if there's a minimum amount of connectivity. So this, I think, also means some robustness. If, for example, we kick out here a few edges or we add up more edges, we might get many more edges, for example, from some probabilistic graphical model tool that might give these dependency graphs or provide us some first network representation of the data. So as long as the bottlenecks between the clusters are sufficiently pronounced, it doesn't really matter that much if there's how many edges are within the cluster. Of course, as long as we can route or route enough flow over the boundary edge.
This brings me to another interesting idea, because other thing I've been playing with in the past few years has been measures of like network robustness, like how to identify critical nodes or edges in an infrastructure. And I kind of guess that with the flow-based method, you could also use your measurements like count the flows, but instead of trying to extract the clusters, you would be trying to extract kind of like the criticality or relevance of certain nodes or edges as a measure of like vulnerability or robustness of the system itself.
Yes.
Super cool.
I mean, this flows. The flow, for example, when we solve our primal-dual, when we use our primal-dual method, we get also flow values. So we solve a dual flow problem, and the amount of flow or the kind of the headroom of the flow value on the edges, which are the dual variables. So the dual variables in this dual problem are flow values. The more they are away from the capacity, so each link has a capacity, which is exactly the weight of the link. And the more away it is, the more robust it is against changes. So the more it could take on flows from another edge that gets kicked out by some reason. But yeah, so very interesting. Yeah, the robustness aspect is also worth studying more detail, definitely.
Another idea that comes to mind, I could talk about this all day. We're going to let you go soon because I think you need to get to bed. Everybody else needs to get lunch, and I can just live by myself with my ideas. Is that if you are trying to learn what's like the correct cut in terms of the boundary of the flow, maybe even modifying the graph, like if the solution is unclear, like seeing what happens if you kick out certain edges, kind of like making like modified versions of it might also be helpful. But yes, this is super interesting. I am so thankful. I sometimes have difficulty explaining to the doctoral students why studying network flows is relevant, even if you're really into other stuff. But I think this is a very, very good wake-up call on why you can, it's such a versatile tool. Like if you're not really trying to solve a flow problem, you can still use a flow algorithm and arrive at so many places. This was lovely, but I am going to let Gerardo Palafox do the formal parts of displaying our gratitude as an institution for all this lovely information, and then we'll let you go have your weekend. Palafox, adelante.
Thank you very much for your talk. The Universidad Autónoma de Nuevo León, through its Facultad de Ingeniería Mecánica y Eléctrica, presents this certificate to Alexander Helmut Jung for his participation as speaker in the conference Network Federated Multitask Learning in the second 2021 conference series of the graduate program in Systems Engineering. Thank you everyone for joining us, and next week, Professor Iris Martinez will talk to us about routing problems. Thank you.
Thanks a lot.